So, shall we start?
Yes, I think we can start. Oh, hi.
Hello, everybody. This is the next episode of our lovely seminar, Prague Seminar for Mathematical Physics, as you already know. And today, it's my big pleasure to introduce Svatopluk Krysl. He's a local researcher in the Mathematical Institute of Charles University, and he's the next in a quite long row of our local researchers, and he's gonna to say something interesting about Penrose twistors and their generalizations.
Yeah, thank you very much. To I'm a researcher, I will not give a research lecture, I will give an overview lecture, about twistors and spinors of Penrose, about its approach to physics. So we shall introduce tensor algebra for spinors. Then we shall mention the twistor equation and its solution. And then probably when we will have time, we shall mention the mathematical result of Penrose on the correction of self-duality and complex geometry. And even if there will be more time, we shall mention the Penrose word transform. Yeah. So the Spinor approach to physics gave, as far as I know, for example, convenient coordinate description for several specific space-times, and then also quantitative description of family of geodesics related to shears and further properties of geodesics. But I will be very brief, and I will introduce the spinors, twistors in the Penrose setting. So it's actually not so easy to understand the notation of Penrose. Yeah. So but it's very precisely defined. Yeah. However, on a couple of pages at least, on quite a lot of pages. Yeah. So then I will give a literature. Further, I had the pleasure when I was as a researcher interested in spinors and twistors, I had the pleasure to read the, local newsletters from Oxford, yeah. And so there are many contributions handwritten by Roger Penrose. They are from Vladimir Souček, kept from Oxford, who shall have been there for the time, and who spoke about the Penrose twistors quite often a couple of years ago. So, what are spinors? I will write with spinors in dimension 4. So it means it can mean more things. We have a 4-dimensional manifold as a model of the spacetime. So spinors are in physics very often defined as a projective representations or at least double-valued representations of specific groups of, namely in the physical setting of SOPQ. So first is projective, or this is very easy and quite known, I hope, or double-valued representation of SOPQ. It's called 1-3. So special orthogonal group in P plus Q dimensions with respect to the bilateral form with P pluses and Q minuses. So double valued, so it's often omitted in current mathematics. Usually to avoid double value things, one has to take double cover of the domain and then to make those things single value. So typical picture is a square root to make it single value, which is double valued. To make it single value, one consider the Riemannian surface of the square root. Check or not. actually draw somehow in this way. It's too much. So we have a paper. We must cut out an axis where the square root is not defined, which I will not do. And then we shall turn it in an appropriate way. Yeah. So I guess you know that I take a double cover of the domain somehow, subdomain, and then I can make the square root, in this case, single value. I take here the plus, and here I take the minus of the square root with respect to this cut out axis, cut out some part of it. So, and the similar thing we do with this SOPQ. In order to have a single valued representation, we define a double cover, and the double cover is denoted as spin PQ, and it will be, by definition, connected double cover of SOPQ. And then we can define our representations as not as double valued, but as single valued. This even cannot be single valued when this is injected. This is 2 to 1, and this must be 2 to 1, and then it left some appropriate non-trivial. So in dimension 4, however, one doesn't need to construct it within the framework, which is classical for mathematics as Clifford algebra. So we does the following observation, which is really crucial for twistors and spin-off. So we have a flat space R13, and which we can actually identify as the space of Hermitian matrices. That is A buffer denotes conjugated transposition of a matrix, and we denote this isomorphism by J. So really, this how to define it? It's classical to define it in this way. So minus x4, and here is the minus. And in this way, we get linear isomorphism, as you can check, onto Hermitian matrices. So then the advantage of this description of the Minkowski of this R1 to 1 3, so it's R4 with bilinear R4 of signature 1 plus and 3 minuses. So we can then define following morphism of semigroups. We have a group of matrices 2 by 2 and matrices 4 by 4 real and complex. And we said, sorry, I did a mistake. It should be only 5.
It's on your eraser, it's there if you want to.
I erase it.
No, we.
This one. This one. Then.
Yeah.
So we define it in this way. Phi A of a matrix should be a matrix. So we evaluate 4 by 4. We evaluate it on a vector in the following way. Yeah. So we take JV, we get a matrix, and we multiply it from two sides by this A. And we do it in this way. So we get a 2 by 2 matrix, and if it is Hermitian, we can pull it back to get the vector. So it's immediate to check that the matrix inside is Hermitian, because if you do dagger, the order reverse, and then you get dagger, it's A, and then you get JV, dagger, which is JV, because JV is Hermitian. JV is Hermitian. And then you get A dagger, which is the same. It's written inside, and then I do the J. Then I do the J back inverse. Yeah. So no, actually it is Hermitian. Yeah. So, okay. So further observation, which is more crucial, is okay. There is also some small things, some small computation, which I thought you wouldn't believe, but this is a actually one can check if this phi is what I mentioned. Sure, what I mentioned, it is a morphism of semigroups. You just must plug in phi B and evaluate it on this side and this side, and we will check that it's true. Maybe I shall omit it. There is one trick. Just plugging in J compose with J -1. You can do it. I hope I will not bother you. If you see further, this is one of the most important computation in the Twistor theory, spinors. Yeah. So I'm just using the definition of phi. So I take this JV, AB, and pull it back by J. That I do the inverse here. And now, for example, you may do this. BJ, and A is missing. So then I put it here, okay. For example, in this way. I will write all the brackets. Yeah, that's sorry for that. You should write more brackets if you need it. I will omit it, sorry. So, and then you see that this is A of this, which is phi of B on B, and I must write this A dagger, and this inside is phi I. Yes, on this vector J strange. B J phi BV. This is the phi BV. Yeah. Yeah, no, it is correct according to that. According to this formula. And now it's either VAB, V result V is VA circle composition with 5A. So it is a homomorphism of semigroups, and we restrict it to a subgroup. This phi we restrict to subgroup SL2C, which you probably know that is the it is a group of all the matrices 2 by 2 with determinant 1, which is easily seen to be subgroup here because everything is it's invertible because of the determinant. And the determinant of product is product of determinants. So we restrict it, and it's a matter to find that the image is of algebra, easy algebra, to find that the image is a subgroup, yeah, because we can take phi A, phi B, and this is phi AB. If you maybe multiply phi A times phi B, we get phi of AB because phi is a semigroup morphism. And then what next? Phi A minus inverse. What that? That's just phi A inverse because A times A inverse is 1. So we should check the phi A times phi B. It's also in the image, yeah, because this is because of the previous property, and then we must we get easily this for example that actually also this, but this can be written as that. It can be written as that. And from this it follows that phi minus 1 is phi minus 1. I hopefully didn't write it twice, but I forgot the one arrow. Equation equality. So we see also that the inverses are in images of A minus 1 is in SL2C. A inverse is in SL2C, that's easier. By what I mentioned. We have a restriction which maps SL2C onto, by what I mentioned, a subgroup of real 4x4 matrices. And now, further, the last crucial information concern a computation of the determinant of the matrix, Hermitian matrix. And also further information which we will get. So we can compute determinant of this matrix, which is the determinant of, I will write it when we write the whole matrix. If you compute further, you will get to this expression, which is the same as here was minus, which is the same as v times v, the Minkowski, which we know that it's that it is that product. This quadratic form will be space size. So this is the definition. So, and it already means that the image of phi is orthogonal. Yeah? So let's have a look at it. With respect to the Minkowski metric. So result. Minkowski, I should say Minkowski binary form. Phi A B. Phi of A B. Where is A? A is in S2C. Minkowski is by definition is what? Well, by the result we just obtained is determinant of J phi A B. Yeah. But phi is what? Phi is j minus 1 of JV AJV. AJV. Yeah. So only using the definition of phi, which is great. And this is the determinant of A JV. This, which is and no, actually, we must do another type of computation. This is just this is 1 times 1 times the determinant of JV, because and this is just then Minkowski on the R2C, R13. Does it make sense? So the multiplicativeness of determinant and the fact that A is unimodular. This is in the R2C. So we got that phi A is a morphism of the Minkowski bilinear form of the Minkowski spacetime. So phi A is in, by definition of these symbols, in this group, and phi is a map. It's immediate, so it's a matter of definition to see that phi is a map from S1 to C onto 1,3 onto O13. Further, identity and minus identity is mapped on identity on O13. So the group kernel is isomorphic to Z2. So phi is so-called 2 to 1. Yeah, so by homogeneity, it's 2 to 1 on the whole SL2C group. Yeah, so one thing. And what's further fact? What we didn't prove? That it is really a covering, meaning that it's covering of the O13. So that it is onto. And this is what we omit. Yeah, so we omit the fact that it is onto, which is non-trivial. One can do it as far as I know, by considering boosts that this group is generated by proper rotations, possibly changing the orientation, and by boosts and so on. And these two types of elements can be generated by elements of SL2C. And if one is into groups by so-called Iwasawa decomposition here, into maximal compact SO, abelian, and unipotent subgroups, these boosts and orthogonal maps can be proper orthogonal maps of R3 can be generated by some specific formula. So model of the subjectivity, we know that SL2C is spin 1,3. Spin 1,3 is connected. Okay, we didn't do that. Connected. That's easy. SL2C, everybody knows that SL2C is connected. So, so model of the subjectivity, we prove that SL2C is a spin group, which is by definition isomorphic to spin group. Right, connected components. By definition, it should be 2 to 1 covering onto O13. So 2 to 1 we proved. We defined the mapping. We proved that it is 2 to 1 and the subjectivity is left. Okay, so that's the first observation and coincidence of in the twistor theory. So this can be used to define spin-offs. So definition spin-offs. You will have two spin-offs. The space S plus and S minus. Both of them will be isomorphic to C2. Will be actually C2. And the two representations, and you have two representations. SL2C into automorphisms of these two spaces given by just the regular representation and then by contra-gradient. Sorry, I don't know. Which is not dual in this case. Just a matter of definition. These are spin-offs representations. Isomorphic to that you know from Clifford algebras, which are defined in a more complicated way by Clifford algebras, and there is a spin inside in Clifford. These are explicit evaluations of SL2C on C2. These are definitions. For physicists, convenient for people doing gravitation and who want to understand spin particles in gravitation. Want to write equations for spin particles within gravitation. Spin is actually, as far as I know, not easy to see or it's not a consequence. The existence of spin is not consequence of non-quantum mechanics. Yes, so it's quantum phenomenon. So and it's a kind of that's why it's kind of you can say that it's kind of a fusion of gravity and parts of quantum mechanics. So it's not the unification, probably unified, yes, but I don't know it. No, so these are spinors, abstract indices. Yeah, this is what make the Penrose text interesting, but maybe also not so easy to see. So each vector space over, let's say, over the complex numbers will be given its labeled partner. So we have H alpha, which is nothing but this, the Cartesian product. We will have also many ways how to introduce it. But it forces us in some way to have a set of labels. And so on. And we define this space as that. And any vector which somebody may not like will have its labeled object, which will be nothing but B alpha, and for that we will make sums and multiples. Yeah, B alpha plus W alpha will be just V plus W alpha. So this is, I should say, nothing too much mysterious, but we didn't do classically to have coordinates. We must take a basis, which we haven't done yet. So these are abstract indices. One can paraphrase it probably in this way: abstract indices, not with respect to any basis. They are not coordinates. Yeah.
We can sum only when we have the same object, right?
Yes. There is operation of permutation of indices, which I will not go into because it needs copies. But everything is very clear. It's defined in the, as I mentioned, extensive book, Penrose. I didn't mention the name. Penrose, Rindler. Spinors and space-time. Volume 1. This is volume 1 that I also want to do. And here even Penrose even speaks about modules over rings, not only about vector spaces, but modules over rings, which are then if they are reflexive, so-called reflexive. So and some reflexive, you need some W's, probably if I remember it, but so there is what will be a tensor PQ type is of type PQ, but of labels alpha, gamma, and zeta to theta. It's object of that. just omits the labels and then one plugin. To be more specific, yeah, already it is a map from the Cartesian from the product. Cartesian product. To the K. Yeah. So this is Q. Any multilinear map from this. You can make Cartesian product of sides. They have natural vector space structure even for more than 2 indices and so on. So one can calculate, but one can trace back the labels. The labels. That's important. I mean, the indices, which are not coordinated. So if you see that, you can understand it probably more. So then the coincidence of Hermitian matrices, I mean, equality of Hermitian, the space of Hermitian matrices and the space R13 can be used for defining this isomorphism. I don't know, following isomorphism as an abstract indices like level.
Sorry, can I interrupt you? There is a question from the audience, but apparently one participant had a problem with the mic. So the question regards the definition of spinors when you defined row plus and row minus. Could you please explain it more? How does it work? Because there appeared a matrix, and question actually is how this matrix appeared there.
Probably it refers to that I omitted to write once the form as a column, as a row. So in the definition of spinors, there is one S plus called as a column, and the minus, I think it's as a row. I didn't write it actually. So in the second formula, the S plus with index down should be understood as column. Yeah. As a row, sorry. I will write it. N minus. Hold N minus. Of the C2 of considered in this way is this. So we will not go into all the conventions, but I should have mentioned it, yeah, because there are also primed and unprimed indices. This is the second issue of the twistor theory. So, spinor theory divergent 4. I define S minus, S plus, S minus down. These will be also isomorphic to C2. I will go into coordinates. This will be understood as columns. This shall be understood as rows. This setting really. And then one have a so-called Hermitian conjugation. So to any element from S minus S plus, we assign element this Hermitian conjugate from S minus by really changing by conjugating the entries. this is denoted in this way. Actually, yeah, I should say briefly in this a bit utilitaristic or some effective, efficient way. So these are the finishes of the right-hand side. Yeah. So this is the Penrose notation that he primed and or dotted. He dots the indices on the right-hand side. Yeah. So if he does the Hermitian conjugation, he dots the right-hand sides. The indices at the right-hand side. So there are many more conventions, but they can then give some I think they can give some geometric picture, for example, spin structures on manifolds. We will now use this dotted things a bit further. So let us equip a set of labels, and these are for spinors. These Latin letters, enhanced by the dotted Latin letters. We have just more labels for the spinors. And how do we express this J? This map J, making so I told the Hermitian matrices isomorphic with R4. We do it by Pauli matrices, which Penrose calls the Infeld-van der Waerden matrices. So let me have a look how it works. Show you how it works. So let us. These will be such tensors with respect to the basis. Already, we must go into basis. So I will recall the definitions P2 and B. Difference as follows. So we define some matrices, and now we define any dotted, undotted prime number, dotted, undotted bispinor. For any dotted bispinor, we define this vector. So that is construction works. It's a different question. There are further issues in spinor algebra and the tensor algebra for the spaces S plus, S minus, up and down. Yeah. Indexed, and namely, what's interesting, what one as a differential geometer probably doesn't think of usually, is that the spinor representation I define is invariant with respect to the symplectic form, because SL2C is the same as SP in this case. Yeah. SL2C is the same as symplectic matrices. But the representation theorists know, okay, these representations are so-called symplectic representations. And that's why SL2C has actually two non-isomorphic serial representations, complex. One is homomorphic, one is anti-homomorphic. So this is connected to something known and unknown at one place, because what can be there can be more things mentioned. I will just write this formula. I will just write this form. I will not go into further coincidences which are there, but I need to say. For connections, yeah, how do we come back? We have a connection indexed by this. This is by definition that. Let us have a manifold, or we can stay in R4. We can have coordinates xi on the R4, and then we can have vector fields dd xy, dd xa, dd xa, and we define this. So this is coordinate dependent from all maps. Yes. And how do we come back from connection to by spinorial object? By this infeld van der Wedden, then again. Yeah. Actually, I should mention it maybe. Let us denote, but we choose a coordinate. Yeah, I cannot do it in the coordinate-less manner. So it's let us take epsilon. So these are the definitions. So this is a map on S plus minus into S plus minus, which Penrose denotes by epsilon. Yeah. So typically it's omega, but he denotes it by epsilon, and by this epsilon he rises and lowers indices. So and I recall the following convention, which is when I have an index, upper index. So we are back in the abstract labels, not by in the spinorial Latin things. Zeta until theta. And I would like to lower the index. So I will put this lowering here. And here I put an element which is not there, which is upsilon. Upsilon. And this is the lowered version of this. Or I can call it gamma. Rather call it gamma, way better. So, yeah. So I have a tensor with alpha and beta, and if I repeat two indices, I sum over it, which I didn't say as well. It's easy. There's everywhere is Einstein summation convention to get invariant objects. And here I sum over alpha and I put gamma here. So this is convenient notation, and so it is lowering is by epsilon writing at the left hand side, and lowering by assuming of the further index in the sense that alpha is further to alpha than gamma is close to alpha, and then by rising of indices, we mean let us take the same as well. We would like to rise zeta, so we shall write zeta, and if we rise up the index, we rise it by a more neighbored index. So epsilon is left at the left hand side, and this zeta is closer than this psi. No, to sell it. So is it understandable, this convention? Yeah? So epsilon is all the time left, and rising is by the further by the index which is not too close to the, which is further than the index with which you want to be lowered. And by raising its actually the
Right,
opposite
so
way.
then the signs are correct in
Yes,
this way. So
these signs
the
are
plus
correct, yeah.
sign.
Because you are right, this is what maybe you see for the first time, but that the epsilons needn't be symmetric, and they are not symmetric.
No,
Epsilons are
exactly.
not.
Yeah.
If the one rises by metrics, not only by Riemannian matrices. By matrices of Riemannian numbers, for example. So these are some conventions. So what we did in coordinates, it doesn't seem so miraculous that to a vector we assigned a bispinor, so which has some possibility to be a matrix. V times V dual is isomorphic to the case of is isomorphic to the space of matrices. So this is actually based on the isomorphism J, which is here it is by no means miraculous in coordinates, but you saw that when seeing that this J isomorphism is actually true. That was a recollection, and now we shall come to this. To the following observations. So first application of the mathematics and the conventions would be, let us consider this matrix, which you know from electromagnetism and I shall write an anti-symmetric matrix. And here it is symmetric. So this is denoted in this way. Let's EY EIs there'll be functions. Let's say it in this way. Functions in R3, B1, B2, the same, and they are sufficiently smooth to form a smooth vector field when put together. Just for defining these, just B is B1, B2, B3, meaning Bx is B1, X, B2, X, B3, X, and so on, the same for E. Then what we define further is that thing. If you work with the scalar algebra, I will probably be able to define it yet. So we just make a spinorial version of this bivector via the Pauli matrices. And we get that. And for this field, we can get this equation. Which is this equation, where phi, and this is what I probably forgot already from my lectures on physics, or I cannot give them any meaning, which I would like to, is this equation. The equation is easy, but that takes this really bispinor. This would be 4 spinor for indices. So spinor is 1 with 2 undotted and 2 dotted indices. Yeah.
So that is just this F, A, X, B, Y as a name in physics like literature. So
I forgot. This is probably it doesn't. This is what is it called? This thing. Strength? No, I don't know.
Yeah, field
Strength.
strength.
Strength of electromagnetism. Strength. Yeah, this is strength, and this will be spinorial description. This is the contraction of that. No. This is a bispinor, and this set of equations for A assumed over X prime and B, and we are in spinor algebra. So we are in S plus or S minus. So they are 2-dimensional isomorphic. Set the isomorphisms this way. Also important to. So these X are for 2 indices and B also for 2 indices, labeling this basis in C2, which I will not mention. So, which I mentioned maybe. A is 0, 1, depending in which C you are. So, and these equations are miraculously proved, can be proved to be equivalent to the Maxwell equations for vacuum. Yeah, so this can be checked by some symmetries as far as the infill under the Lagrange symbols. Remember. So now number E is 0, nabla B plus minus D0 E and nabla E plus minus D0 B and nabla point B as vector 1 is 3. Yeah, that's what I thought about. So this set of equations, you can check that it is equivalent to these 4 equations, which E is C1, E2, B3, B is B1, B2, B3. For example, you shall work with the connections. You will get example is nabla 1, 1 dot shall be under the Latin symbol of this kind. You will get that it is just 1 over 2 square of T0 plus 1 over 2 square V3 and 1 0 dot is 1 over 2 D1 plus 1 over 2 D2. Polymerizing well in this. So I can play with these definitions by going from vectors to spinors to achieve some interesting result, which is the beginning of the Penrose of what is important for this approach. So you can write further equations. These Maxwell equations for vacuum are called Bernoulli's. I must have a look. I haven't worked in that for a long time. Equation for massless field of spin 1. Yes, so it's basically just for one. Sorry, field. It is by no means dual of some endomorphism of Schwarz spaces and the duals. I don't know this. Rotka fields in quantum field theories, it's not quantum field. I'm not sure about the terminology yet. So further equations we can write, and finally we go to the twistor equation. So this is Maxwell or helicity or spin one field equation. This is ABC spin 3/2, 3 indices. And this is helicity one spin massless equation. So this is probably the Dirac, let's say Dirac equation for massless fields, but it's actually more precisely for the bio-neutrino. The same. Majorana neutrino. By Penrose. So we can go further. So this is a systematic actually form. Yeah? This is what you see as a mathematician or physicist. I have one index. So I wrote it in a wrong order. 2 indices, 3 indices, and the connection is the same. We have 2 indices, spinors times. This is what we didn't mention actually. So, and the equation, which we will have hopefully time to understand it that one. I swap now the indices which I can do. I have to introduce that, and I have to introduce further notation, which would take a lot of, which would take a lot of time. Actually, also in this one. That's right. Let's write it in a full spin only one half at the beginning, not in this general. So, so we have a scalar field. From that to convention to that. We can make a differentiation. Then we can take this and that. But it then goes to and this. And one is dotted, so this is dotted. And the convention says that. Antibody convention. Plus.
What is story there?
Sorry, slowly. Yes, it should be.
What is the round bracket? Sorry.
Yeah, this is symmetrization.
But
I mentioned
this is different. One is not.
Yeah.
Yeah, that's the definition of twistor problem, you know. You can symmetrize this thing.
No, so for me it's a convention on these spaces. I can change them with the labels. But maybe I can postpone this question. It can be very difficult to explain the labels. Yeah, sorry for these details. We say that two tensors are the same on H alpha beta and H beta alpha, but the domains are different. H alpha beta is strictly speaking not H beta alpha, because once we make Cartesians with alpha and then with beta and then it's beta and then with alpha. So one should speak about the permutation of indices. Yes, it can take time as far as I remember. So I will define it. So if you are lost, you can really, in a sense, that I didn't define it. You can really think of that null as numerical indices. You can transfer it to 0 and 1s. If it doesn't make sense what I write now. So it's not possible, yes. We take 30 pages of the Penrose's book, yes. On the other side, he obtained a Nobel Prize 2 years ago, so maybe it's worth of reading. Maybe not. I must write in that. So not enough. I think it should mean that. It should mean this, yes, probably. There are further identifications. So no, I must say, write it in the numbers here as coordinates. Here we have no time to explore the formalism. So we did some first steps, one half of the formalism regarding spinor algebras of Penrose. For example, what doesn't make sense now is to add these things because indices are swapped. You cannot add H alphas with H betas by our definition. So there is further definition of permutation of indices, which I cannot explain, unfortunately, which makes you able to add this. Yeah. So no, unfortunately, think in really numerical indices 0, 1, 1, n. Not everything can be explored. Yeah. Explained. So, but what is interesting? Hopefully it's. Yeah, and what's even worse, that I am reversing dots and unders. That's why I made a mistake. So sorry, I don't need it there. So the equation we shall write is this one. And this is the twistor. No, we don't have problems with dots and undots, which was even wronger. We have only problems with copies. And this is the twistor equation. You can write it in coordinates by this Pauli matrices, by this prescription of connection in spinos, but it will be quite complicated. So fortunately, we can solve it in the case of the Minkowski spacetime, so on R13. Let's see. Namely, first, so solution on R13 this flat Minkowski metric of that equation. Yeah. The connection is really differentiation with respect to the flat, to the, let's say, ordinary vector fields, to the coordinate vector fields. We don't have any manifold and so on. So that, as I thought, first observed the following information. Any scalar of this kind can be written in this form. This is probably also a bit important to know, to define, because it's quite often occurs in the Penrose program and spinor program, I mean. So, and we have spinor with 3 indices. The symmetrization already is 0. So it means that the spinor itself, the trispinor with the connection, is what? Is anti-symmetric. So the first thing is that this is anti-symmetric in AB.
Yeah.
Yeah, so blah blah. So A is anti-symmetric. Sorry, the whole object. The whole object is anti-symmetric in AB. Now, I still consider that this phi is a solution of the Twistor equation. And let us differentiate that for the second time, the Twistor equation. So I have blah blah CC phi b is 0. These things can be commute because of what?
Flat derivatives.
Yeah, because it's a curvature 0, the Minkowski, so they commuted and they are coordinate vector fields. So this, I don't know, we don't have this term because the bracket is 0. Yeah, okay. So we can commute on this and also in the spinorial version because this is just the spinorial is the isomorphism of this. And this is the that. And this is the Twistor equation as well.
Yes.
For other index, but we sum over it. There can be many things can be strange there, yeah. So for depending on the person perception. So this is then symmetrization.
We'll
Right?
see though this time.
Thanks.
No.
Symmetrize in this way. No. And this is anti-symmetric in CB. for the same reason. Because tensor is a sum of symmetric and anti-symmetric part all the time. All the same reason as here. So anti-symmetric in CB. And now we have a tensor anti-symmetric in CBA, B, C, and with respect to all three indices. And it is a tensor on S2, on C2. So now this is in lambda 3 S C2, which is 0. And so if you have what is maybe not easy, what is maybe not clear. So we have a 3 tensor, which is anti-symmetric with respect to AB. And then it is anti-symmetric with respect to CB.
It's fully anti-symmetric.
CAB. And now I should prove that it is anti-symmetric with respect to AC.
Yep.
So I do the anti-symmetric with respect to AB. C probably W. Yeah. And now I see the anti-symmetry in the passive interpretation of AC. Not of the positions, but of the labels, yes, which is also somehow important. We are not speaking about position, but about letters. So, I mean, the convention of Penrose, it can be seen from more sides. And then this is 0. Yeah? So we have exterior 3 tensors with 2 degrees of freedom. This is 0. So we actually achieved that the whole tensor A, C, B, phi B is anti-symmetric from that. This is the interesting information. So this whole tensor is anti-symmetric in AB, anti-symmetric in BC, and no anti-symmetric in ABC. This is what I wanted to, what I should have taught. So this is 0, and this can be then integrated twice to get that it has all the linear solutions, which we don't have time too much to write on. So I will write on the result.
Yeah.
So we just so this second derivative is constant. So we have a linear, I should say, affine functions. So phi b is x, some xi, if you round in the bispinorial notation, pi plus omega b constant, and this is denoted by this circle. And I should have a look how I wrote it for me.
Oh.
Yeah, there are several conventions. I chose the more. This one, to write it more understandably. Let us evaluate this phi in a point of the Minkowski spacetime. So here we have this time pi b. This is the linear part, and this is the affine part from the constant, the constant solution. And then we have this information. Penrose writes it a bit further, in a more, you will often see that, which is just the use of the lowering convention or rising and lowering convention. And here he puts I. So I'm imaginary. So these are all solutions. Yeah. So you have really not symmetrization, because about symmetrization you don't have information about all differentiations, but only the symmetric ones. But you have about all, and then you integrate twice 0 to get constant and linear upright. And this space, it's called the Twistor space. Yeah. This is by convention. It is not dotted. I will write it by this, but probably this is S minus. We cannot distinguish it by what we thought we had until now. So this is the Twistor space, yeah. So the space of solutions of the Twistor equation on Minkowski spacetime, and it is also a representation of SL2C. It is isomorphic to S plus S minus down, and it is isomorphic to that. And now my aim was to put it into a perspective of representational theory of more general groups, which we certainly don't have the time to yet. So we can decompose some representations and see twistor operators. This one is a specific case of some operators which are, by the way, known as Stein-Weiss gradients for this equation, which are elliptic complex, which form elliptic complexes. And to see further symmetries. So we actually only introduced that what Penrose did in the 60s, or on there. So he rewrote vectors into spinor by this coincidence. We learned how to manage the indices, probably. The connection of Hermitian matrices and vector we mentioned, but not maybe on the level of indices too carefully or too slowly. And then we introduce the space of solutions. Maybe further coincidence in that one. Multiplying tensorially of spinors, we get this, which is the complexified Minkowski R4 times C, so for complexified Minkowski spacetime. And this is also that. The Hermitians of C, which are real over C, I mean the real vector spaces. So this is further coincidence connected, but disconnected to twistors because here is a sum, here is a product. And maybe the very last I shall mention something which is actually quite difficult to understand here. So these solutions are 4-dimensional. The solution space of the Twistor equation is 4-dimensional. That's a complex vector space. Now, the complexified Minkowski spacetime is also C4, from R4 times C with C4. And so if we would like, and we maybe have some hints, some reasons to interpret the solution space as a constituent of the Minkowski space itself, the complexified Minkowski space. So this can be understood as these particles forming this Minkowski space, which maybe can be refused by, and this is like Phlogiston as well. It's hard for me to do Phlogiston theory for space-time. There are certainly people who understand that. So it should be anti-Kantism, as I read according to some philosophical work on Stanford. this idea. And probably I was saying not so really qualified things. I will stop here with the interpretation of our space as a matter, solution of the twistor space. But Penrose did more, for me at least, quite miraculous things from in mathematics as well. So, well, maybe about that next time, so we have time to understand that.
Okay, thank you very much. We're a bit over time, but if there are questions.
Maybe I have one question concerning the twistor isomorphism. You explained to us isomorphism between spin 1, 3 and SL2C, but there is something what is also referred as the twistor isomorphism, and it is isomorphism between, or maybe covering between spin 2, 4, if I'm not wrong, and SU22. Like,
No, this is too complicated for me to explain it explicitly. This is maybe easier SO2 to R to SL2 R to spin 1 or something like that. And this is like I can say only reference by words. I cannot say mathematically. SU22, it should be what the unitary group of plus plus minus minus spacetime, and this is the conformal.
Yeah.
Both are conformal. No, I don't know the definitions.
In this representation, or when you take representation of this bigger spin group, your twistors gonna be irreducible representation instead of this sum of
Yes,
pi.
yes.
Yeah. So this is maybe.
But I forgot this SU22. Is it connected to? Certainly connected to quadrates. Yeah. Well, I don't know. I forgot this isomorphism. How is it proved? This is proved in a similar way as we did by the matrices 2 by 2. SU2, but also by quaternions. Yes, by quaternions. Probably quaternion have symmetric and symmetric. I don't know it.
I try to prove it, but it's well known how to prove. It's not that easy to provide.
Yeah, well, certainly connections SU22, CO, I mean, conformal orthogonal of in 1, 3, spin 2, 4, and these ones.
This
I cannot solve the proof here. I've been back for 15 years in this spinorial things. Interesting things are also the word transform, Penrose word transform, time correspondence, and it is solution of Dirac on simply connected sets when going to the so-called twistor space. This is real mathematics. And then self-dual connections, half, say the name is half while flat, how it corresponds to complex geometry and integrability of some bundles of H in Penrose. So these are really deep things in mathematics. This was some empathizer for regarding indices and known equations, how to rewrite it. That it somehow underline the normal world, physical world. So thank you.
Yeah, thank you very much.